Yeah, so I want to talk about mathematical ideas or concepts, or maybe better, even results behind machine learning. And with this, I essentially understand deep learning and neural nets. So neural net is really what I'm trying to get a little bit of interesting mathematics. And so maybe let me just give a survey. I suppose more or less everybody knows about neural nets, but still let me say a little bit what is there, and then what kind of questions in this context I want to address. Okay, so what a neural network. So what is this? I mean, this is essentially a function from high dimensional space into, let's say, R of a specific form. Okay, so I mean, what I'm really looking at are neural networks, or maybe more precisely, probably a fully connected feed-forward neural network. Okay, and so this is a function. I mean, essentially, this is a function. Let's say f, which goes from usually a high dimensional space, and high dimension is really what will matter, because it's really about high dimensions where we are going to talk about, where interesting phenomena happens. So it's a function from this space to, let's say, R. I mean, I could also here go to a more dimensional version, but I mean, having here more dimensional version is just a collection of functions from this to R. So I mean, usually, if I have functions from from some dimension to some dimension, then this here is the crucial thing. Here it's just a tuple of functions. Okay, but this is not an arbitrary function, but it's a specific function, usually of a specific form. And maybe I try to draw it here just to collect all the things. Okay, so I'm going from, let's say, R to the P. So P is usually the dimension of the space from where I start. So that's the data. I mean, a vector of the data which I consider. And so I have, let's say, I have a vector of entries. So this is my input. And this is essentially, so X is in R to the P. And that's my data vector. So I'm dealing with datas. So usually I try to use P for the dimension of the data. Okay, I mean, everybody uses different notations for the dimensions which are around, so I try at least to keep a consistent way. Okay, and then you usually embed this into a space of maybe bigger dimension. And so maybe let's say I go to R to the M. This might be a different dimension. And then I mean, I usually do this by linear mapping. So I'm taking a matrix and embedding this in a linear way. Okay, and then essentially I iterate this. But the crucial thing is that I also compose this with nonlinear mappings. Okay, so I mean, if I have done this here, let's say with a linear mapping, let me call this. So I mean, this is somehow embedding this here in a linear way. Everything is connected with everything. Then I go to the R to the M, but then I also apply a non-linear mapping, but in a specific way, namely component-wise. So I mean, essentially, I stay here, and maybe here I apply entry-wise to my vector fixed non-linear mapping. Okay, so that is my first layer, and then I go on and I do essentially the same. I embed this here, and I might change the dimension here from each layer to the next one, but I want to keep this. I mean, I want to keep it simple. So I say here I always stay on on the level M. So I go here again to R to the M. So here I have a mapping. Let me call it W1, a linear mapping, which means a matrix. A matrix from linear mapping from p-dimensional to m-dimensional. And here I do the same from m to m with another matrix. So yeah, I do here all my connections with a W2, and then I apply again my nonlinear mapping here So I stay essentially here, but I change this thing here entry-wise. Okay, and then I go on like this, and I might have arbitrary or fixed number of layers. And deep learning usually means that I have many layers. So the deep really means to how many layers I have, but it's just a number of layers. And so maybe the last one, let me call this the last one WL. So I have here L layers. Okay, I go here again to R to the M. Maybe my nonlinear mapping, and then in the last step I go down to R, and there I apply a linear mapping to this. Okay, so here I go essentially down to R, and that's my output. So here I'm in R. That's my output, and I mean this is my function. That's what I'm doing. I have an input here, a vector in R to the P. I apply my matrices, then this nonlinear mappings entry-wise, again matrices entry-wise, and so. And in the last step, I'm projecting it down in a linear way to R. Okay, so that's essentially that's a neural network, and this is what I want to understand what it does. Okay, and so I mean what one has to understand is essentially, I mean two things. What does it do with input vectors if I have chosen all my parameters here? But of course the crucial thing is that I want essentially to produce a net which does what it has to do. So the training usually means to finding the right parameters here. That's of course the most interesting thing. Okay, but of course mathematically, first step is really to understand how does such a thing, maybe if the parameters are given, act on the input, and what does it produce as an output. Good. Okay, so that's maybe, so what I have here, I mean those guys here, I mean those are the layers of my net, and they are the usually hidden layers. I don't see them. Okay, and in this case I think I would have L layers. Okay, and this number of layers, that's the depth of my network. So this here is the depth, and deep learning refers to the depth. Okay, but then of course I also have somehow the width of the net, namely how big is this M here. And that's usually the width, and okay, usually this is also very large, and this means I have a wide network. Okay, and controlling somehow large M's, large width is somehow easier, or maybe that's better thing I can control than making this L here big. So this direction here, that's the width of my network, and usually if this is large, then I have a wide network. Okay, so maybe in a sense a lot of what I'm talking about is more about wide networks than deep networks, but of course one has to understand all of this. Good. Okay, so I mean here I'm putting in a data, one vector, and usually I mean I have not only one vector, but I'm making measurements. So I have a set of vectors which I'm putting in, and which maybe has some correlation or whatever, and I want to understand what happens with this if I feed it through the network. So usually instead of just looking on one vector here, I have a collection of datas, and let's say I say I have n of them, and usually I put them into a matrix. So I mean instead of having a vector here, I consider then maybe a matrix where I have n of those vectors. So each of them is a p-dimensional vector, and now I'm putting them n of them into a matrix, so I have an n times p matrix here. So this is then in R p times n. So it's an it has n columns and p rows. Okay, and that's my data set matrix. That's the measurements, or that's my input which I want to understand. So that's here my data. Set matrix. Yeah, okay, good. So that's essentially a neural net. And what, I mean, of course, it depends on many things. So what I have here is essentially these linear mappings, which I do in each steps, which I have called W's. So I mean, I have W1 up to WL. Those are linear mappings, so matrices. So in the first step, it goes from P to M. Okay, in the last step, maybe I should also give it a name. I mean, I call this here WL plus 1. So all of them are matrices. Of course, this is just a vector, a row vector. Okay, and the others are mappings are M times M matrices. But those are linear mappings. Which, of course, I can identify with matrices. So they are given in terms of matrices. Okay, if I only have this and I don't have these nonlinear mappings, then it would be a linear neural net, and this is easier. This is somehow easier to deal with, and the nonlinear mappings somehow they seem to make the interesting stuff. Okay, so I have here in each step I have a nonlinear map, maybe which I call so this map from here to here, maybe I call it sigma twiddle. So this acts on my vector with m components, gives me another vector with m components, but usually this is a very simple one because it acts just entry-wise. For each component of the vector, it acts on this with a given nonlinear mapping. So I have one nonlinear mapping, and this acts on each of the entries. So this so what I need for this is a nonlinear map. But this is only a map. Let me call it sigma, which just acts on a component from R to R, and I apply to my vectors component-wise. So applied component-wise on vectors in R to the M. So this means the sigma twiddle which I have there, I mean usually we would also just write sigma, but maybe as a mathematician I like to be precise. So the sigma twiddle, so this is a map from R to P to the RP, which actually, I mean on a vector, it just takes the sigma of the corresponding entry. Okay, so that's my mapping which I have here. Good, okay, so that's the neural net, and that's something which I want to understand. And of course, I mean this mapping from p-dimensional space to P of this form is determined, of course, by the W's and the sigmas. And of course, I can make more complicated versions of this by having, I mean, I could change the nonlinearity in each step. I can also change the dimension in each step, but I want to keep it simple in some sense. Okay, so this is determined. So this is a function of this form. This form, as I have it there, and it is determined by, of course, I mean all the input which I have there, and I mean, of course, one is this nonlinear map, and this is usually chosen from the beginning. Okay, so there are canonical choices for this nonlinearity. Sigma from R to R, and this is usually fixed, and for example there's this ReLU map, or there are specific ones which often used. So this is usually fixed, and e.g. one prominent one is this ReLU, rectified linear, what is the U standing for? Unit. Okay, so this is just the mapping which is 0 here, and it's linear here. Okay. Yeah. Good. Okay. And then, of course, it's all the matrices which I have there. So all the matrices W1 up to WL plus 1. And those are usually called, I mean, they are the parameters of my model. I mean, this sigma is fixed, but those are the guys on which I want to, yeah, to find the right ones. Okay, so they are my network. Parameters, and they have to be chosen in the right way, because I mean I really want the function to do something specific, and and it's not that I know exactly which parameters I should choose for this, but the net should choose it by themselves via training. Okay, so that's what one wants to understand. And the problem is, okay, I mean this is a kind of simple function, and if the dimensions are quite small, I mean you can just see what it does, but the problem is that the dimension of my data is very high. Okay, that makes it somehow complicated. Okay, so that's the problem. So the data sets, our data set is high dimensional. Okay, so P is large, and what we want to do is, of course, we want to have functions which somehow characterize or distinguish specific data sets. So what we want is to characterize or distinguish data sets by such functions. Okay, and for example, for example, this data set can be the vector of a high dimensional picture. Okay, I mean I'm choosing here the entries, the components are real numbers. Of course, they can just be plus minus 1, or they can be something between 0 and 255 or whatever. But maybe here I'm just saying they can be real numbers. But of course, they could also be discrete versions of this. But so, for example, I mean X, my data, could be a vector of a picture, high resolution picture. And of course, I mean then P is, okay, 1000 is, okay, now probably in millions or something like this as the data we have to deal with nowadays. Okay, and so, I mean, so the sets which I want to consider are something like the information about, for example, pictures, a vector of, let's say, a high resolution picture. And then I want, essentially, I want something like this, that I can distinguish different kind of pictures. For example, cats and dogs. So, for example, I would have to have something that I have, let's say, subsets in this space, C and D, where C are the pictures of cats, and D is the pictures of dogs. And what I would like to have is a function which distinguishes me those two sets. So we would like to have a function f which goes from these pictures to real numbers. But now let's say essentially I want to distinguish it. So let's say I want to have a 0-1 decision whether it's a cat or a dog. So such that f of x is 1 or 0, or maybe close to 1 if I have a cat picture, and 0 if I have a dog picture. Okay, so I mean that's something which I would like to have. But of course the problem is that we don't really know how to define this function, because we don't really know how can we describe a picture of a dog and a picture of a cat. So what should we, I mean, how, if I have a picture, how should I decide whether it's a cat or a dog? If I would know this, then I could, then I could just tell the computer what it should do. But we don't know this. We cannot really distinguish this. And I think in the good old times, I mean, that was really how you tried to teach the computer how it should distinguish pictures, by trying to tell the computer how you know that it's a cat or a dog. So what should you look at? But this doesn't really work so well. And what works somehow well is that, yeah, that computer should essentially learn this function. We are not telling the computer what the function is, but we are just giving it some examples, and then it should adjust the parameters such that it works in the end. Okay, so I mean, we do some training of such a network. So we start we are initialized by random in some random way or so, and then the computer should learn, change the parameters such that this function really does in the end what it is supposed to do. Okay, and I mean this this looks okay somehow ridiculous, but in the end it works very well, and it's really, I think it's still a mystery why it works well. Okay, so yeah, okay, so this is somehow the big mystery, and yeah, we want to understand a little bit about this, and yeah, I mean, it's those are functions in very high dimensions, and they look very complicated, as if they could do anything on the parameters. And so how can you say anything specific about this? And somehow the point is that because your dimensions are very large, you have some kind of control what happens. Okay, so maybe something let me say. So what works well in this picture here, yeah, I have this somehow these hidden layers, where I have all this many. I apply this nonlinearity, and I apply this matrices, and then I have the last step, where essentially I'm projecting down from a high dimensional space to a low dimensional space, and this last step is somehow, this is not so bad to control. So what I have is essentially I go from RP, I go to RM, by essentially doing this composition of the nonlinear map with a linear map. Then I go to another RM and so on. I stay in these m dimensions with these nonlinearities and the linear maps. And in the last step, I'm going down with a matrix, a linear mapping to R. So this just means I take the inner product with some vector here. Okay, and usually, I mean, I think the idea is that yeah, this last vector here, this somehow is the vector of features of your objects. So the idea is, I mean, here you should have got some special features of your picture. Okay, and then in the end you take some weighted version of the features. So the idea is the network should have learned here really something, as maybe we do if you're looking on pictures of cats. So what should we see? So maybe I mean we should I don't know, eyes and maybe a fur or whatever. So those are features which you would like to see, and maybe they should show up here. Okay, and then in the last step we just take a weighted average over the features to decide whether it's a cat or a dog. Okay, and so if those guys here, if everything here is somehow fixed, and the learning only happens here, then this is a kind of somehow easy problem. Then it's a kind of linear problem. So I mean, if essentially I have those guys here fixed and go from here to here, then what I have here is a kind of embedding, and this corresponds to having to kernels. So this is usually what is given by kernel methods, which means I'm embedding my datas into maybe a high dimensional space in a specific way, nonlinear way, but this is somehow fixed or given. Okay, so this is an embedding which comes from somewhere, and doing this usually corresponds to doing kernel methods, and then it's only in the last step that I go down here, where then maybe I should choose for the last step the right parameters. Okay, but this is a linear problem, and this can be easily controlled. So this is somehow easy to do. Okay, yeah, but the problem is then that essentially the network is not learning the features, but this should be given somehow from the beginning. Okay, so kernel methods usually don't learn the features, but it seems, I mean, feature learning is very essential for the success of neural networks. Okay, and I mean, in this context, where we go for high dimensions, if m goes to infinity, actually, in this setting here, you converge to some kind of kernel. So namely, there's something which is called a neural tangent kernel, which has become quite popular in the last years. So this is, if m goes to infinity, then what you have here converges to a specific object, which is neural, which is a kind of kernel, which is called neural tangent kernel, and which can help to understand you a couple of things. But the problem is, I mean, it's a kernel, and it's not changing during the learning process. So okay, you are not learning features, and somehow, okay, this is a nice starting point, but it's of course not good enough to explain why everything of this works. Okay, but I mean, this is something maybe about which I also want to talk at some point. Good. Okay, but yeah. Good. So I mean, the really interesting thing for those neural network is, of course, the learning process. And I mean, it really works better as you would expect. Yeah, maybe there's also this problem of over-parameterization. So I mean, usually you have here your p-dimensional data, and okay, you have n of them, which you want to learn. So you're given n of them, and then the network should learn how it deals with this. But then, of course, you should also do predictions. Then you get new pictures, and you should say, the network should say whether it's a cat or not. And of course, usually, I mean, the classical learning theory tells you, I mean, if you have too many parameters, then this is actually bad for learning. Because if your memory is so big that you just can memorize everything you have seen, then you don't learn anything more. But then, okay, you cannot make predictions. So if you do interpolation for a number of points with polynomials, of course, you can take very high-dimensional polynomials to interpolate 5 points. But then, I mean, between the points, you will have very, very weird stuff. Okay, so it's much better to take a polynomial of degree 4 or 5 for 5 points. This gives you a much smoother interpolation. Okay, and that's the idea. I mean, here you have many more parameters. I mean, here in each step you have m squared parameters, and if your thing is deep, you have really many of them. So you have much more parameters than you are learning here in your data set. So the conventional wisdom would be that actually such a thing is over-parameterized, and it should not be good for making predictions. But astonishingly, it does. That's maybe it's one of the big mysteries at the moment. So why does this really work so well? So in particular, if you over-parameterize. Good. Okay. But so that's things we want to understand. But maybe before we go on those hard questions, where I'm not sure that I mean, mathematically we don't really have good answers for them. Maybe we have some things we can understand, but maybe we should first start with trying to understand what does such a function do on input vectors. How does it change them? Okay, and so maybe in particular we should now also think about how do we actually model our data set. Of course, I mean, if our data set is given by cat pictures, I mean, I don't know how to describe them. So how should I mathematically deal with them? Okay, so what? So how we can really how we can describe our data sets is actually by probability distributions. So we have a collection of points which we would like to describe, and we do this in a probabilistic way. Of course, essentially I could say I have my pictures of the cats, and I take the uniform distribution on this set. And then I want to make statements about this. This gives me then probabilistic statements about what happens in this context. Of course, I don't know the set of all cats, so the uniform distribution on this set is also not a very concrete thing. Okay, so but I will replace this by other distributions where I can work better with, and maybe I can also do at least abstract statements, even if the distribution is not so explicit. Okay, so our data sets are high dimensional, and yeah, we want to describe them by probability distributions. Okay, and I mean probability distributions, in particular in high dimensions, yeah, there are not so many where I really can do concrete calculations, but there's a very nice one, namely a Gaussian distribution, where really one can calculate a lot of things. So that will be our basic characterization, which gives us a lot of ideas and hopefully also results. Okay, so yeah. So we have high dimensional data sets, and I want to model them by probability distributions in R to the P. Okay, so maybe the most canonical would be a uniform distribution on the set on which I'm interested, but uniform distributions, okay, it's not so easy to deal with. So if I have more distributions with a density, I can calculate more. In particular, I can calculate really concretely for Gaussian distributions. So one of the things which we really have to understand will be Gaussian distributions in R to the P. So that's, we will talk about this quite a bit. Gaussian distributions. And so this means my vector in the R to the P has components x1 up to xp. Okay, so I'm not using the lower index because this somehow I want to reserve if I have copies of my x. Okay, so those are real numbers. So my vector x has p components, and the Gaussian distribution essentially, I mean the main information is contained in the mean, so the average, and this is the average of each of them. So this is a vector of the averages. So this is the expectation of the first component up to the expectation of the last one. Okay, and maybe in many situations, maybe I can assume this is equal to 0. So let me do here. Let's say this is 0, and then the other information are the second moments. I take the variance or the covariance between those guys here. Okay, so that's a matrix. So if I assume mu is equal to 0, then the main information is in the second moments of this vector. This is the covariance matrix. So this is a p times p matrix. It's the covariance between those p guys here. So let me call it sigma. So this is a matrix where the ij entry is the expectation of the product of xi and xj. So because the mean is 0, this is the covariance between those two components. So this is a vector where I and j are running from a matrix where I and j are running from 1 to p. So this is a p by p matrix. Okay, so this is the correlation between those guys. Okay, and so of course from a maybe practical point of view, of course assuming that I have a Gaussian distribution here is not very realistic. So I mean data which you use or so are of course not of this nature. So for example, I mean for example, if I would say I have here independent entries and each of them has a given variance, of course that's not what you have in your data sets. If you have a vector of the pixels of a picture, of course those guys are correlated. If you have a picture of a cat or so, I mean many of them have a big correlation and others don't. So it's clearly not a Gaussian distribution which is anything close to let's say the uniform distribution on this set of the cats. Okay, but so somehow the interesting point is that actually we can compose such vectors which have a Gaussian distribution with some specific functions, namely Lipschitz functions which are smooth, which I can control, and then I'm transforming this Gaussian vector into a vector which doesn't have a Gaussian distribution anymore, but which still has a lot of properties which one can show, which one has for Gaussian vectors. So what I get then are concentrated random vectors. So these are vectors which still have this kind of concentration, which we will see that we have for Gaussian vectors. And those guys are maybe much better, or they are somehow closer to real data. So actually, I mean, we will essentially work and calculate for Gaussian vectors, but the point is that many of the properties which we see there are preserved under taking Lipschitz functions of the entries, and then I'm destroying the Gaussian distribution totally, but I still preserve interesting properties which I can control. Okay, so I have my Gaussian vectors, the ones which I can write down nicely, and I can also calculate many things, but they of course are not really anything close to real data. But I can compose this with Lipschitz functions. I mean, Lipschitz functions are functions which are kind of continuous. I mean, functions of all the variables, but in a controllable way. And then what I get are now vectors where I don't really know explicitly the distribution which they have, but they still have many properties which I had before. So I get concentrated random vectors. And they are somehow, they should be somehow closer to real data. Okay, and maybe in particular, okay, those are really things which show up in applications. I mean, there are these GAN things. What is it? Generative adversarial networks, which are very popular, which can be used to produce fake pictures of cats and dogs, for example. Okay, and they essentially start from a Gaussian distribution and apply Lipschitz functions like this. I mean, they apply neural networks, but the neural network is composed of functions like this. So I mean, what you produce there are vectors of this form. Okay, so this means this here really is something which should be closer. Yeah. Sorry. I mean, it means that those vectors they concentrate if you apply functions to them. I mean, essentially, Gaussian vectors do this, and Lipschitz functions of them. To give you concretely other ones is not so easy. Yeah. I mean, if you have here a vector, okay, and then you apply a function. You make a new vector out of them by taking functions of all the entries here. Of course, you will get a totally different distribution. Okay, but this distribution has this concentration property. I mean, we still have to talk about what I mean, essentially, it means that if you take Lipschitz functions from this vector, that they concentrate. So that essentially they are almost always very close to the average. So that's the concentration property about which we will talk. I mean, one of the big themes of the whole thing is that in high dimensions you have concentration, which means that if you take functions of variables, of many variables, that actually this function is more or less constant. So it's very close to the average value. But of course, this depends on an underlying probability measure. So you have a probability measure on your vectors, but if this probability measure has this concentration property, then it means if you apply Lipschitz functions to this vector, then they will concentrate. So Yeah, okay. So, but those are the things which we are going to talk about more. So that's really the main things. Yeah, okay, but maybe let me say a little bit more about this statistical idea. I mean, that I have here an input distribution. Let's say I model this by Gaussian distribution, and then of course this is determined by the mean. Let's say the mean is 0, so it's determined by the covariance matrix. The covariance of the vectors is the crucial property. Okay, but now of course usually we don't know the distribution. We make measurements, so we see samples of our vectors, and from this we want to get as much information about the distribution. Okay, so so our knowledge about the data is given by measurements or observations. So we do samples, and so let's say, we have n measurements. So we have observed n instances of our vector. Let's say, so we have x1 up to xn, and each of them is in Rp. Okay, so that's the data which we are given. That's the thing we can work with. Okay, and of course, usually the idea, in particular in statistics, is that if you have your samples, your observations, they should give you estimators for the real underlying properties. So you should get estimators for the covariance. So we assume, I have here independent copies of my Gaussian distribution in R to the n. This Gaussian distribution is described by the covariance matrix, and I want to estimate this covariance matrix from the concrete data which I have here. And of course, what do? I take the corresponding quantity here for each vector. One vector, of course, I can take this product here. Then I approximate this expectation by taking an average over my measurements which I have made. So this means from this I can look on an estimator for the covariance matrix, my sample covariance matrix, which I call sigma hat. And there I'm averaging over the quantities which I get from each vector. So for each vector, I can look on xk I, xk j, doing this for all I and j from 1 up to p. So I'm just taking, so for each fixed k, for each of my observation, I just do this combination here for all I and j. So I get p times p matrix, which is essentially this kind of covariance version for this one vector. Okay, but then if I have n measurements, I average. So I average over this. I sum over this and average 1 over n. So this is the averaged version. So this is my sample covariance matrix. Okay, and of course I can also write this maybe a little bit more nicely, more in terms of products of vectors or matrices. So namely for each fixed k, what I'm doing here, I'm essentially, x is a vector, so it's a column. Okay, and what I'm doing here is essentially taking the matrix product of let me see, of a column with a row. Okay, so column with a row gives me a matrix. The other way around, it would be the inner product. But here I'm doing it in this way, that what I have here is xk times the transpose of xk. So this is my vector. This is the transpose of the vector. So this is the vector is a row. And this is the column version of it. If I multiply it, I get the matrix, exactly the matrix with those guys as entries. Okay, so you see I can write it like this. And then if I'm summing over these things, essentially I can say what I'm doing here is taking the same kind of product of the matrix, of the data matrix. So this actually is 1 over n. And then the summation here is really that I'm doing the product xxt, where x is the collection of the n vectors. So as I had it before. So this is x1 up to xn. So each of them is a vector of dimension p, and I'm putting them into this matrix. So I have n times p matrix. And if I multiply this like this is exactly what I'm doing here. Okay, so it's just writing it in a nice form, and really, I mean, that this doing those things into a matrix is meaningful because I can really, the interesting quantities, I can write them in a very nice and compact matrix form. Okay, anyhow, but what I really have is this thing here. Good. Okay, and now of course the idea in statistics is that if you make enough observations, if your sample is big enough, then you can really recover the underlying property. So in classical statistics, you would say I make sufficiently many observations, I make n big enough, and then this guy here should approximate the covariance of my distribution. Okay, that's classical statistics. So there, P is fixed. We have a fixed set of quantities in which we're interested, but then we send n to infinity. We make infinitely many observations, or a large number of observations, and then this P times P matrix, sigma hat, which I get from my observation, converges. So this here means converges, so if n goes to infinity, to the real x. Good. Okay, but that's the classical frame where you can make as many observations as you want, but that's not the setting we are in, because I mean what we have is we have a number of observations, we have many of them, but we also, the P is also large, and actually P and n are of the same order. So you have many data, and you have on the same order of observations. Okay, and usually, I mean, you cannot say, okay, I make more and more observations to get in the classical regime, because okay, you really have to go very high with this n usually. Okay, so that's not what you have. So the point is that, I mean, this is nice statistics, but it's quite useless for our considerations. And the question is, can we replace it by something? Is there anything else we can say? And the point is that actually, in the regime where we are, if n is proportional to p, we can really make rigorous statements. So there's a different regime where you can make precise statements. So I mean, so what we are dealing with in this big data business, but in particular in this class here, because I mean that's really what we want to understand, is the setting where p is proportional to n. Okay, so again, we say we make a limit. We say that the situation which we consider is somehow an approximation of an infinite dimensional situation, but not the infinite dimensional situation where p is fixed and n goes to infinity, but one where p and n both go together to infinity, such that the ratio is fixed. Okay, so I mean, those are of the same order, and this regime is actually a regime which we can control. That's the whole point of this. So really, we can make very precise statements. So it's a different regime than a classical one. So this means this guy here will not be close to this guy, but it will be of a form that we really can control it and say how it depends on this guy. Okay, so I mean this. So this is different from the above, a different regime. But the point is, and okay, maybe it's more also it's more complicated in a sense, but the point is we still can control it. We can make precise statements. Huh? Good, yeah, okay. And so, I mean, I want to give you maybe some ideas of this. Yeah, so what, and I mean, of course, in our net, okay, I mean, I also have here, I have here P and I have also M, huh? And I have N. Huh? So N is the number of observations which I make, P is the size of my data, and M is maybe the higher dimension where I embed everything. Huh? Okay, and so what we are dealing with is a situation where all those, let's say P, N, and M are of the same order. Huh? Okay, huh? And so we assume that P and N and M can go to infinity, but in the same order. Huh? So the ratio of them goes to a fixed number. Huh? So maybe all of them are the same. Huh? Yeah. Okay. And of course, M going to infinity, you see, is really that I'm looking on wide networks. Huh? So I make them wide. Huh? Okay. So L is not, I'm not telling about L here. So L is a bit more, okay, I'm not saying that the depth also should go to infinity in the same sense. Huh? So usually, I mean, the depth is maybe fixed, might be big, but it's not going to infinity like this, or the roll-off of the depth is not so clear. Huh? Okay, good. So it's more the width which scales here, and where we can make precise statements. Good, okay, and so I mean, all of this is related with this concentration phenomena in high dimensions. And so now maybe I want to show you some slides which gives you an idea. Huh? I mean, essentially in high dimensions, things concentrate. Huh? Okay, so I suppose some of those things you have seen and so, but maybe some not. So, but let's see. And here you see, I mean, maybe one of the overall titles is the curse and the blessing of high dimensions. Huh? So high dimensions, in one sense, are bad. That's the curse. That's usually in statistics, it's okay, big frame. But I mean, I think we come more to the conviction that actually there are also many good things in high dimensions which we can use for us, and that's the blessing. The curse of high dimension means that high dimensions are really very large. Huh? And so, I mean, if you want to sample things there, okay, it's impossible to really sample the distribution of something. Huh? Okay, so I mean, yeah, high dimensional spaces are quite large and quite empty. Huh? Okay, so that's the curse. So for many algorithms, statistical methods in high dimensions, they don't work because things explode exponentially, and you would have to visit too many points in your space which you cannot do. Okay, but on the other hand, the blessing is, and I mean, I want to convince you of some of those blessing things, that actually that many things show a deterministic behavior. Huh? That's this concentration idea. And so actually, I mean, this is this idea that if you take smooth one-dimensional functions of your high-dimensional vectors, they usually concentrate. Okay, and that's the good thing. That's the concentration phenomena in high dimensions. That's what we will talk about. Okay, and so maybe let me give you just a few pictures of this concentration of random vectors, okay, and such things. So maybe concentration of random vectors is something which you have seen or know. I mean. Yeah, okay, and so I'm looking here on the Gauss distribution. Huh? So, I mean, this is the one-dimensional Gauss distribution. Huh? Okay, and so I have here, I take a vector which is Gauss distributed with variance 1, and I draw the histogram, and I take here 100,000 samples. Huh? So, I mean, even in one dimension, to get a good picture of the normal distribution, you have to sample really many. Huh? Okay, maybe you see it with a little bit less, but to get a smooth, nice picture of the Gauss curve, you really have to sample many of your vectors. Huh? Okay, and so now, but the point is, I mean, this thing is nothing which we want to look at in high dimensions. What we want to look at is the length of a vector. In one dimension, I mean, the length of a vector is a mapping from Rp to R In one dimension, of course, the length of a vector and the vector itself is not a big difference, because in R, either it's positive or negative. So I mean, it's just that the length of the positive vectors is just the vector itself, and here on the negative side, they get flipped over here. Okay, so the distribution of the length is essentially just twice the distribution of the Gauss itself. Okay, so in two dimensions, in one dimension, I mean, it's still okay. Nothing interesting. Okay, but now in two dimensions, so here is a two-dimensional Gauss. So now I take a vector in R2. So both components are now Gauss. They are independent. I'm choosing them independent. And usually, I'm normalizing my distribution here so that the averaged length of the vector is equal to 1. So the variance of each component is 1, in this case 1 over square root of 2. Okay, so you see here the distribution, again 100,000 samples of such a vector, and now I take again the length. So the length is now a one-dimensional thing, and you see, okay, I mean the length here is, I have plotted it between 0 and 2. Of course, it extends to infinity, but okay, you see it's mostly, so in this, the length is somewhere here. Okay, so you see something like this. So it's still spread out. Okay, and if I now go to higher dimensions, of course I cannot plot anymore this here. I mean, for a three-dimensional vector, okay, I would have to plot it in 4 dimensions, which is already beyond my possibilities. But the point is also that, I mean, I would need really many more samples to get a picture which shows essentially the distribution in higher dimensions. Okay, and so what I'm consider now is those kind of picture. I'm just looking on the length of my vectors. Okay, and so here, and probably everybody knows or has heard that, I mean, actually I have a concentration of my Gaussian distribution on the surface of the unit ball, which means that the length of the vector concentrates around 1. So I have normalized it that the average is 1. Okay, but usually, I mean, I could have a wide distribution around the average. So here you see in P equal to 1. Okay, you see, I mean, actually the length is not even close to 1. Okay, in P equal 2, so that's the same picture which I had before. But now if I go higher, so this is in 5 dimensions, the length, you see it's centered around 1, but it shrinks and shrinks more. So for in 20 dimensions, 80 dimensions, 320, and 1000. So this is a 1000-dimensional vector with a Gauss distribution, and now you see essentially it concentrates. The norm concentrates on 1. So of course the vectors themselves, their distribution. So this means they are lying somehow on the surface of the sphere in this dimension. Okay, which of course is very high dimensional one. So they are not concentrating themselves because they are distributed over a big sphere. But if I'm looking on their lengths, this is really something which concentrates. And that's the main idea of this concentration, that if I'm looking on functions, like Lipschitz functions, I mean, like this, of my vectors, they will concentrate. The vectors themselves, they don't concentrate. I mean, they're still spread out over a very large thing, and it's very hard to find them in this high-dimensional space. Okay, but for functions like this, I have this concentration. That's the idea. Okay, and so maybe another thing is this statement: if I take 2 independent vectors, Gaussian ones, they are nearly orthogonal in high dimensions. Okay, in low dimensions, so if I take p equal to 1, 2 Gauss vectors, I mean, either they show in the same direction or they show in the opposite direction, which means they are either parallel or anti-parallel, which means if I take this normalized inner product between the 2 vectors, so this is the cosine of the angle between them, then I have just plus and minus 1. So either they are parallel or they are not parallel. Okay, in 2 dimensions, okay, it looks more like this. So this means still there are many who are close to parallel, or close to anti-parallel, close to parallel, but there are also some which are close to being orthogonal. So I mean, in the plane, of course, you have vectors which are orthogonal. Okay, but not a majority of them. Okay, and now if I go higher in 5 dimensions, so you see now it goes more towards the 0. So they're becoming, more of them are close to orthogonal. And again, if I go higher and higher, so p equal to 20, 80, 320 and 1000, you see now it concentrates around 0. So 0 is the average value here, but it's also concentrates around this. So 0 was always the average value. I mean, even if I have plus and minus 1, the average is 0. But plus and minus 1 are very far away from 0. But in high dimensions, I mean, everything gets closer and closer to 0. Okay, so that's maybe the idea. And I mean, those are things which we are going to try to prove in a rigorous way, with these statements. How do we formulate, and in particular, how do we prove such things rigorously? Good, okay, but maybe, so this is about the random vectors. So maybe those are things which some of you have already seen, but now maybe let's go to this estimation stuff here, because this might be closer to the data. Okay, so I mean, we have, let's see here. Okay, so let's say we want to estimate a covariance matrix. So say I take here a Gaussian random vector in R to the P. I make the components independent, and the variance, okay, I'm not taking that all of them have the same variance, but let's say half of them have variance 1, half of them have variance 2. And then the covariance matrix is diagonal, but on the first half of them I get a 2, on the other half I get a 1. Okay, so the eigenvalues, usually I mean I'm looking on the eigenvalues of the covariance matrix. That's the main thing. So the eigenvalues of this covariance matrix, half of them are 1, half of them are 2. That's the real covariance matrix of my distribution. Okay, but now I make observations. I take now n samples of such a situation, and then the question is, what do I see then? Okay, so now I take, let's say, p equal to 100 and n equal to 100. So I make 100 observations of choosing samples, independent realizations of this vector of length 100. Okay, and then I'm calculating this matrix, the one which I have written down here. That's my estimator, the estimator for this guy. And then we see a distribution like this. We plot the eigenvalue distribution, and you see, I mean, you don't see the 1 and 2. 1 and the 2 are the real eigenvalues, which are hidden in this distribution. But what we see is a distribution like this. And now the question is, I mean, do we understand this, and is this of any use for us? And of course, I mean, the classical statistic tells us if we make this n here bigger and keep p fixed, then of course we should converge to eigenvalues which are sitting at 1 and 2. So maybe let me do this. So now I fix p, still is 100. So I always have a 100 by 100 matrix, and I calculate, these are always histograms of the 100 eigenvalues of this 100 times 100 matrix. But this matrix is given by averaging over more and more of those guys. So here I'm averaging over 1000, and still, okay, you see maybe 1 and 2 are now more prominent, but it's still not so clear. Then for 10,000, now you see you have a kind of separation between 1 and 2, and here is 100,000. So you see I have go very high to really see something where I can maybe optimistic that 1 and 2 are the right ones. Is there more? No, that's it. Okay, so that's classical statistics. Okay, but I mean, we don't have 100,000 observations or samples. So what we have are these 100, and we cannot really make more. And so the question is this picture now of any use, or can we still understand it? And so what I was saying before is that this is actually now an approximation of a situation where we still go to infinity, but we go to infinity in a way that p and n both still are equal. Oh, so this is somehow an approximation of a situation where I have P and N equal, but maybe bigger. So now I have pictures where I make the N bigger, but P is still the same. So these are now 500 by 500 matrices. For 1000 is this, 2000 like this. And you see, you have a smooth picture, and this is a picture which we can really describe in a limit. There we are able to make precise statements how to get this curve. So there is a limit curve. I mean, it's a smooth curve in a limit. I mean, it doesn't resemble 1 and 2. I mean, in the background, there's still 1 and 2 in the background, but this here is somehow a function of this, but a function which we can control and calculate. And then actually, I mean, our situation for P and N equal to 100 is not so far away from this. So I mean, the limit really, it's good to know the limit, because this picture here really tells us something. So if I observe this, then of course I have two possibilities. I'm saying I describe this by classical statistics, but then N should be very large. But I mean, then the N which we have is too far away from the very large which we would need, because I mean, 1 and 2 in this picture, we just don't see it. Okay, but what we see is that we are actually close to the situation where we go with N to infinity, but P goes to infinity in the same spirit. And this is an approximation which we can control. It's not given by sigma. I mean, we still don't see the 1 and 2 directly here, but in principle, we know how from the 1 and 2 matrix we can calculate this guy here. So we have a kind of understanding of this. Good. Okay, so that's I mean what we are looking here at, those matrices, the sigma matrices, those are random matrices. In particular, those are Wishart matrices. And so what we are looking here is the distribution of Wishart matrices in a limit, and this is what is called the Marchenko-Pastur distribution. So those are things which we are also going to talk about and really try to understand how to calculate those things. Okay, but maybe another thing which is maybe also interesting in this context, going even a bit further, is this signal plus noise models. So let us look on the same situation. So again, let's say I have a vector of dimension 1000. So I have 1000 components, and I want to say that actually one of them is really a signal. So this is a component in which I'm interested, and the rest is just noise. And again, I say here, half of the noise has eigenvalue 1, half of it has eigenvalue 2, and then 1 has a variance which is equal to C. Here I have put C equal to 1, which means I'm back to the one before where I don't have a noise. Okay, so I mean, the real eigenvalue distribution is 1, 2, but the one which we observe, if I take P is equal to N is equal to 1000, is this curve here, the Marchenko-Pastur distribution. Okay, which we can understand. Okay, but now the point is, if I now I change one of these components to having really a signal behavior. So it should have an eigenvalue which is bigger than 1 and 2. So I'm choosing a bigger one. Let's say I'm choosing 7. Okay, I mean, this is very big. I mean, the eigenvalue is just, there's just one eigenvalue, just so that you can see it. I have put a bigger bar here. So I have, let me see, I have 499 eigenvalues here. I have 500 I should here. Okay, and I should have 1 here. Okay. Okay, I have 1 here. Okay, and now if I do with this, calculating this, so will I see somehow this one eigenvalue? I mean, this is the signal which I really want to observe. Can I still see it in the noise which is produced by this finite dimensional, by this situation here? And if you do the simulation, you see that actually you get those eigenvalues which you had from before, and then you get an eigenvalue here. Again, it's just one eigenvalue. Just I have plotted it with a bigger bar so that you can see it. So I mean, the signal, the real signal, has variance 7. Okay, but here you observe something around 9. Okay, so you really see it, but it's not at the same position where you would expect it. In the same way as the 1 and 2s, which are sitting here. I mean, you don't see them here, but they are smashed. They are. You have a noisy version of them. Okay, but somehow this this one eigenvalue is not just mixed into the noise and disappears as you would expect. I mean, it's just one of 1,000 eigenvalues, huh? But still it's sitting here and you can observe it. Okay, and now if you move here closer to this 1 and 2, I mean this will also move. So here, if c is equal to 5, so you have one signal eigenvalue sitting at 5, and then you do this calculation here, then you will see that you still see one eigenvalue sitting outside here. So in particular, those eigenvalues here, they are really very strict. I mean, they are sitting here, and there's not one of them which is just sitting out somewhere. So which you could then also think it's a signal. So I mean this here is also a very rigid situation. So you get this distribution, and the eigenvalues which you observe are just really sitting inside this distribution. There are no outliers there. And if you really see something here, it's coming from the signal. Okay, so here maybe it's a situation where c is equal to 4, and then you still see something. But now you see you are moving closer to the edge of this noise spectrum here. And now if you go further in, then this will disappear. It will disappear in this here, and you don't see it anymore. So if I have now c equal to 3, then you don't see an additional eigenvalue. The one has moved inside this bulk here, and you cannot distinguish it anymore. So there you don't see a signal. Okay, but if you are far enough from here, then you really can see this. So that's also something which we will try to describe. In particular, maybe also, if we observe. If you observe something here, okay, the real eigenvalue is sitting here. Maybe that's the one which we would like to know. So we should know how to go back from here to here. What is the relation between the position of this one and this one? Okay, but that's things which we can understand. And that's also things which we are going to do. Okay, so that was my survey on things I want to do. At least those are things which are clear that I want to do. Of course, I also want to do more on understanding, training, and over-parameterization and feature learning or not feature learning. Okay, but I'm not sure whether I can really do or whether I can understand it. So we will see how far we can go, and maybe if there's feedback from you, maybe also interesting new papers in this direction which have mathematical statements on this. So I'm quite interested in this, and of course I don't know all. It's the literature on machine learning is also in high dimension, so you can get lost very easily. So if you know what you're looking at, okay, you find something, it's concentrated, you have your concentration bubble, but okay, other people are living in a very, very different regime of this high dimension. Okay, good. Okay, so I think that's it for today.